The night sky has always held mysteries that stretch beyond what our eyes can see and our minds can comprehend. But what if I told you that the universe is far stranger and more astonishing than we've ever imagined? Hidden within the vast expanse of space are phenomena so extraordinary, they defy everything we think we know about reality. Picture this: black holes that swallow light, galaxies colliding in a cosmic ballet, and stars that explode with the power of 1 billion suns. These aren't just distant wonders, they're forces that shape the very fabric of the universe, and in turn, shape us. Why does this matter? Because every time we uncover one of these cosmic secrets, we take another step toward understanding our place in the grand tapestry of existence. So, let's journey together into the unknown, where the rules of physics bend and the impossible becomes possible. This is 30 unbelievable cosmic phenomena shaping our universe, and it's about to change the way you see everything. Let's start with the ultimate cosmic enigma: black holes. These aren't just dark voids in space. They're regions where gravity becomes so overwhelming that nothing, not even light, can escape their grasp. Think of them as the universe's most powerful vacuum cleaners, pulling in everything that ventures too close. But how do these cosmic monsters come to exist? When a massive star exhausts its fuel, it collapses under its own gravity, compressing into an infinitely dense point called a singularity. This is the heart of a black hole, where the laws of physics as we know them break down. Stephen Hawking revolutionized our understanding of these mysterious objects by proposing that black holes aren't entirely black. They emit something called Hawking radiation, a faint glow that causes them to lose mass over time. It's a slow process, but over billions of years, a black hole can evaporate completely. What's even more mind-boggling is what lies inside. Theories suggest that at the core of a black hole, space and time cease to exist as we understand them. It's a realm where the rules of reality dissolve, leaving scientists with more questions than answers. But black holes aren't just destructive forces, they're also cosmic architects. Supermassive black holes, often found at the center of galaxies, play a critical role in shaping the universe. Their immense gravity acts like an anchor, holding galaxies together and influencing the formation of stars and planets. Without them, the structure of the cosmos as we know it might not exist. Yet, despite their importance, black holes remain one of the greatest mysteries of the universe. What lies beyond the event horizon? What happens to matter once it's sucked in? These are questions that continue to push the boundaries of human knowledge, reminding us just how much we have yet to discover. Now, let's turn our attention to something equally fascinating, but far more compact: neutron stars. These cosmic powerhouses are born from the fiery death throes of massive stars, the aftermath of a supernova explosion that scatters stardust across the galaxy. But what's left behind is no ordinary remnant. Imagine taking the entire mass of a star, something that could dwarf our sun, and compressing it into a sphere no wider than a small city, just 12 miles across. The result is a neutron star, one of the densest objects in the universe. To put that into perspective, a single sugar cube-sized chunk of neutron star material would weigh a staggering 1 billion tons. It's a mind-bending concept that challenges our understanding of matter itself. But neutron stars aren't just dense, they're also incredibly dynamic. Many of them spin at dizzying speeds, rotating hundreds of times every second. This rapid rotation, combined with their powerful magnetic fields, transforms some neutron stars into pulsars. Picture a cosmic lighthouse, beaming intense radiation across the universe in precise, rhythmic pulses. These beams sweep through space, and if Earth happens to lie in their path, We detect them as regular flashes of light or radio waves. It's a phenomenon so reliable that some pulsars are used as natural cosmic clocks, helping scientists test the laws of physics and even navigate spacecraft. And then there's the incredible spectacle of neutron star collisions. When two of these ultra-dense objects spiral toward each other and merge, they send ripples through space-time itself, gravitational waves. These waves, first detected in 2017, confirmed Einstein's century-old prediction and opened a new window into the universe. The collision of neutron stars doesn't just create gravitational waves, it also forges heavy elements like gold and platinum, scattering them across the cosmos. In a way, the jewelry you wear might owe its existence to the violent deaths of ancient stars. Neutron stars also serve as natural laboratories, offering scientists a glimpse into matter under conditions that are impossible to replicate on Earth. At their cores, the pressure is so immense that protons and electrons merge, forming neutrons, hence the name. This extreme environment allows researchers to test theories about the fundamental nature of matter and the forces that govern the universe. Yet, despite their incredible density and power, neutron stars remain shrouded in mystery. What happens to matter at their cores? Could exotic states of matter, like quark-gluon plasma, exist there? These questions drive astronomers and physicists to push the boundaries of human knowledge, proving once again that the universe is full of surprises waiting to be uncovered. Now, let's shift our focus to something that's all around us but remains utterly invisible: dark matter. Imagine looking at the night sky and realizing that everything you see, the stars, the galaxies, even the light itself, makes up less than 5% of the universe. The rest, that's where dark matter comes in. This mysterious substance accounts for roughly 27% of the cosmos, yet it doesn't emit, absorb, or reflect light. It's completely invisible, detectable only through its gravitational influence on the universe around it. It's as if the cosmos is hiding a colossal secret right in plain sight. So, how do we know dark matter exists if we can't see it? It all comes down to gravity. When astronomers study galaxies, they notice something strange. The outer regions of galaxies rotate much faster than they should based on the visible matter alone. If only the stars, gas, and dust we can see were holding these galaxies together, they would fly apart due to their incredible rotational speeds. But they don't. Something unseen, dark matter, must be providing the extra gravitational pull needed to keep everything in place. Think of it as the cosmic scaffolding that holds the universe together, an invisible framework that shapes the large-scale structure of everything we observe. But what exactly is dark matter? That's the million-dollar question. Scientists have proposed countless theories, but so far, none have been proven. Some believe it's made up of exotic particles that don't interact with light or ordinary matter, particles that could be streaming through you right now without you even noticing. Others suggest it might be evidence of new physics, a hint that our understanding of gravity or the fundamental forces of nature is incomplete. It's a mystery that has puzzled scientists for decades, and despite countless experiments designed to detect it, dark matter continues to elude us. The hunt for dark matter is one of the most exciting frontiers in modern science. Researchers are using everything from underground detectors to powerful particle colliders in the hopes of catching a glimpse of this elusive substance. Meanwhile, observations of cosmic phenomena like the cosmic microwave background, the faint afterglow of the Big Bang, provide indirect evidence of dark matter's role in shaping the early universe. It's a puzzle that requires collaboration across disciplines, from astrophysics to particle physics, and it's a reminder of how much we still have to learn about the cosmos. Dark matter isn't just a scientific curiosity, it's a fundamental part of the universe. Without it, galaxies wouldn't form, stars wouldn't shine, and life as we know it might not exist. Yet, for all its importance, dark matter remains one of the greatest mysteries in science. What is it made of? How does it interact with the rest of the universe? And what secrets might it hold about the nature of reality itself? These are the questions that drive astronomers and physicists to keep searching, to keep pushing the boundaries of what we know. And as we uncover more clues, we come closer to understanding the invisible force that shapes the very fabric of our existence. If dark matter is the invisible scaffolding holding the universe together, then dark energy is the unseen hand stretching it apart. This mysterious force, discovered in the late 1990s, has turned our understanding of the cosmos upside down. Imagine the universe as a balloon, not just inflating, but doing so at an ever-increasing pace. That acceleration is driven by dark energy, a phenomenon so powerful it makes up roughly 68% of the universe. Yet, despite its dominance, we know almost nothing about it. What we do know is this: dark energy acts as a kind of cosmic repellent, counteracting gravity's pull and pushing galaxies farther and farther apart. The discovery of dark energy came as a shock to the scientific community. Astronomers were studying distant supernova exploding stars to measure how fast the universe was expanding. They expected to find that the expansion was slowing down thanks to gravity's relentless tug. Instead, they found the opposite. The universe wasn't just expanding, it was speeding up. It was as if someone had stepped on the cosmic gas pedal, and no one could explain why. This revelation earned the researchers the Nobel Prize in Physics in 2011, but it also left us with a profound mystery. What is driving this acceleration? One leading theory suggests that dark energy is a property of space itself. According to this idea, empty space isn't truly empty, it's filled with a kind of energy that causes the universe to expand. This concept, known as the cosmological constant, was first proposed by Albert Einstein over a century ago, though he later dismissed it as his greatest blunder. Ironically, it might turn out to be one of his most insightful ideas. Another possibility is that dark energy arises from an entirely new kind of field, one that permeates the universe and exerts a repulsive force. But so far, no one has been able to detect or measure this field directly. The implications of dark energy are staggering. If it continues to dominate the universe, the cosmos could face a cold, lonely fate. Galaxies will drift farther apart, stars will burn out, and the universe will become an increasingly empty, dark expanse. This scenario, known as the Big Freeze, is just one of several possible outcomes. Some theories suggest that dark energy could grow stronger over time, eventually tearing apart galaxies, stars, and even atoms in a catastrophic event called the Big Rip. Others propose that dark energy might weaken, allowing gravity to regain control and pull the universe back together in a big crunch. The truth is, we simply don't know. Understanding dark energy isn't just about satisfying our curiosity, it's about uncovering the ultimate fate of the universe. To do that, scientists are using some of the most advanced tools ever built. Telescopes like the Vera Rubin Observatory and the James Webb Space Telescope are scouring the skies for clues, while experiments like the Dark Energy Survey and the Euclid Space Mission aim to map the universe's expansion with unprecedented precision. Each observation brings us a little closer to solving one of the greatest puzzles in science. dark energy reminds us that the universe is far stranger and more dynamic than we ever imagined. It's a force that defies our intuition, challenges our theories, and pushes the boundaries of what we think is possible. And while we may not know what it is or where it comes from, one thing is certain: dark energy is shaping the destiny of the cosmos. And in understanding it, we might just unlock the secrets of existence itself. Now, let's turn our gaze to one of the most spectacular events in the universe, the supernova. Imagine a star, millions or even billions of times more massive than our sun, reaching the end of its life. Instead of fading quietly, it goes out with a bang so powerful it can outshine entire galaxies. This is the explosive finale of a supernova, a cosmic event that reshapes the universe in ways we're only beginning to understand. When a massive star exhausts its nuclear fuel, its core collapses under its own gravity. The outer layers, no longer supported by the energy from within, come crashing down, but this collapse isn't the end, it's the beginning of something extraordinary. The core rebounds in a shockwave so violent it tears the star apart, hurling its outer layers into space at incredible speeds. In just a few seconds, a supernova releases more energy than our sun will emit over its entire 10 billion-year lifetime. It's a cosmic fireworks show on a scale that's almost impossible to comprehend. But supernova aren't just dazzling displays, they're also cosmic forges. During these explosions, temperatures and pressures become so extreme that they create heavy elements like iron, gold, and uranium. These elements are scattered across the universe, enriching the gas and dust that will eventually form new stars, planets, and even life. In a very real sense, the iron in your blood and the gold in your jewelry were forged in the hearts of dying stars, billions of years ago. Without supernova, the universe, as we know it, simply wouldn't exist. Supernova also serve as cosmic lighthouses, helping astronomers map the vast distances of the universe. Because these explosions are so bright and consistent in their behavior, scientists can use them to measure how far away distant galaxies are. It's a technique called the standard candle method, and it's one of the key tools we have for understanding the scale and structure of the cosmos. In fact, it was observations of supernova that first revealed the universe's accelerating expansion, leading to the discovery of dark energy. But not all supernova are the same. There are two main types, each with its own unique characteristics. Type I supernova occur in binary star systems, where a white dwarf siphons material from its companion until it becomes unstable and explodes. Type Roman II supernova, on the other hand, are the dramatic deaths of massive stars, collapsing under their own weight before rebounding in a spectacular explosion. Each type leaves behind a different remnant: neutron stars, black holes, or expanding clouds of gas and dust that will one day birth new stars. What's truly remarkable is how these explosive events connect us to the universe. Every supernova is both an ending and a beginning, a star's final act and the birth of something new. They remind us that the universe is a dynamic, ever-changing place, where destruction and creation are two sides of the same cosmic coin. And as we study these incredible phenomena, we're not just learning about the stars, we're uncovering the story of how everything, including us, came to be. Supernova are a testament to the power and beauty of the cosmos, a reminder that even in death, stars light the way for the future. And as we continue to explore the universe, these explosive events will guide us, helping us piece together the grand puzzle of existence. From the fiery death throes of stars to the invisible forces shaping galaxies, the universe never ceases to amaze. But among its most astonishing displays are gamma-ray, bursts cosmic explosions so powerful they defy comprehension. These are not just any explosions, they are the most energetic events ever recorded in the universe, unleashing more energy in a few seconds than our Sun will produce over its entire 10 billion-year lifespan. To put it simply, if a supernova is a firework, a gamma-ray burst is the entire fireworks factory exploding at once. These bursts originate from some of the most dramatic events in the cosmos. One common trigger is the collapse of a massive star, far larger than our Sun, as it reaches the end of its life. When such a star exhausts its fuel, its core collapses into a black hole, and the surrounding material is ejected in a pair of ultra-focused jets. These jets, traveling at nearly the speed of light, emit intense gamma radiation, the most energetic form of light. Another source of gamma-ray bursts is the collision of neutron stars, those ultra-dense remnants of stellar explosions. When two neutron stars spiral into each other and merge, they too release a torrent of gamma rays, lighting up the universe in a brilliant flash. What makes gamma-ray bursts so extraordinary is their sheer power. A single burst can outshine an entire galaxy, and its light can travel billions of light years before reaching us. Imagine a beacon so bright it's visible across vast stretches of the cosmos, acting as a cosmic lighthouse from the distant past. These bursts are fleeting, often lasting just a few seconds, but their impact is profound. They've been detected from the earliest epochs of the universe, offering a glimpse into the conditions that existed shortly after the Big Bang. In a sense, they're like time capsules, carrying information from a time when galaxies were young and the universe was still taking shape. But gamma-ray bursts aren't just awe-inspiring, they're also a reminder of the universe's capacity for destruction. If one were to occur relatively close to Earth, within a few thousand light years, the effects could be catastrophic. The intense radiation could strip away our planet's ozone layer, exposing life to harmful ultraviolet rays from the sun. It's a sobering thought, but also a testament to the delicate balance that allows life to exist in the cosmos. Thankfully, gamma-ray bursts are rare, and the likelihood of one occurring near Earth is incredibly slim. Still, studying them helps us understand the risks and prepare for the unexpected. For scientists, gamma-ray bursts are more than just cosmic fireworks, they're invaluable tools for exploring the universe. Their brightness allows astronomers to study the most distant reaches of space, probing regions that would otherwise remain hidden. By analyzing the light from these bursts, researchers can learn about the composition of ancient galaxies, the nature of dark matter, and even the expansion rate of the universe. It's a field of study that bridges the gap between astrophysics and cosmology, offering insights into both the smallest particles and the largest structures in existence. Gamma-ray bursts are a reminder of how much we still have to learn about the universe. They challenge our understanding of physics, push the limits of our technology, and inspire us to keep looking deeper into the cosmos. Each burst is a fleeting moment of brilliance, a snapshot of the universe's most extreme conditions, and as we continue to study them, we uncover not just the secrets of these cosmic explosions, but also the story of how the universe itself came to be. Among the countless wonders of the cosmos, few are as dazzling or as enigmatic as quasars. These cosmic powerhouses are not just bright, they are the brightest objects in the entire universe. Imagine a light so intense it could outshine thousands of galaxies combined, visible from billions of light years away. That's the sheer magnitude of a quasar. But what exactly are these brilliant beacons, and how do they come to exist? The answer lies in one of the most destructive and creative forces in the universe, supermassive black holes. At the heart of every quasar is a supermassive black hole, millions or even billions of times more massive than our Sun. But unlike the black holes we've discussed earlier, these giants are far from dormant. They are actively feeding, devouring gas, dust, and even entire stars at an astonishing rate. As matter spirals into the black hole, it heats up to unimaginable temperatures, creating a swirling disk of superheated material. This disk glows with such ferocious intensity that it can outshine the entire galaxy that surrounds it. It's like a cosmic furnace, burning brighter than anything else in the universe. But quasars don't just radiate light, they also unleash torrents of energy in the form of powerful jets. These jets, made up of charged particles and radiation, shoot out from the poles of the black hole at nearly the speed of light, stretching across thousands of light years. They carve through space, shaping the galaxy around them and influencing the formation of stars and planets. In a way, quasars are both creators and destroyers, sculpting the cosmos on a scale that's almost impossible to comprehend. What makes quasars particularly fascinating is their role as cosmic time capsules. Because light takes time to travel across the universe, the light we see from distant quasars has been journeying for billions of years. When we observe a quasar, we're essentially looking back in time, catching a glimpse of the universe as it was in its infancy. This makes quasars invaluable tools for astronomers, offering a window into the early stages of galaxy formation and the evolution of the cosmos itself. Yet, despite their brilliance, quasars are not eternal. As the black hole at the center consumes all the available matter, the quasar's light gradually fades, and the galaxy it once illuminated returns to relative obscurity. But even in their absence, quasars leave a lasting impact. The energy they release can heat surrounding gas, preventing it from collapsing to form new stars. This process, known as feedback, plays a crucial role in regulating galaxy growth and shaping the large-scale structure of the universe. Quasars remind us that the universe is a place of extremes of unimaginable power, light, and transformation. They challenge our understanding of physics, push the limits of our imagination, and reveal the intricate connections between black holes, galaxies, and the cosmos as a whole. And as we continue to study these luminous giants, we uncover not just the secrets of quasars, but also the story of how the universe itself evolved into the vibrant, dynamic place we see today. While quasars light up the distant reaches of the cosmos, there's another phenomenon that takes us even further back in time, not to the birth of stars or galaxies, but to the birth of the universe itself. This is the cosmic microwave background, or CMB, often described as the afterglow of the Big Bang. Picture the universe as a newborn, just moments after its explosive beginning. In those early stages, it was an unimaginably hot, dense soup of particles and energy. But as it expanded and cooled, it left behind a faint, almost imperceptible whisper of radiation, a thermal fingerprint that still lingers today. Discovered accidentally in 1965 by two radio astronomers, Arno Penzias and Robert Wilson, the CMB was initially dismissed as mere static interference. But this static turned out to be something far more profound, the oldest light in the universe, a relic from a time when the cosmos was just 380,000 years old. At that point, the universe had cooled enough for atoms to form, allowing light to travel freely for the first time. This light, stretched and cooled over billions of years, now reaches us as microwave radiation, a faint glow that fills every corner of the cosmos. What makes the CMB so extraordinary is its uniformity. No matter where you look in the sky, this radiation is almost identical, with a temperature just a few degrees above absolute zero. But within this uniformity lies a treasure trove of information. Tiny fluctuations in the CMB, variations in temperature on the scale of 1 part in 100,000, hold the key to understanding the universe's structure. These minute irregularities are the seeds of everything we see today: galaxies, galaxy clusters, and the vast cosmic web that connects them. They're like the brushstrokes on a cosmic canvas, hinting at the forces that shape the universe in its infancy. Studying the CMB has revolutionized our understanding of the cosmos. It provided the first solid evidence for the Big Bang theory, confirming that the universe had a definite beginning. It also revealed the universe's composition, showing that ordinary matter, the stuff of stars, planets, and people, makes up less than 5% of everything. The rest is dark matter and dark energy, the mysterious components that dominate the cosmos. The CMB even gave us clues about the universe's geometry, suggesting that space is flat on large scales, a finding that has profound implications for cosmology. But the CMB isn't just a static relic, it's a dynamic record of the universe's earliest moments. By analyzing its patterns, scientists can test theories about the universe's expansion, the nature of dark energy, and even the origins of cosmic inflation, a period of rapid growth thought to have occurred just fractions of a second after the Big Bang. It's like reading the universe's baby book, filled with details about its first moments and the forces that shaped its destiny. The CMB also serves as a reminder of our place in the cosmos. That faint glow you see on a static-filled television screen, that's not just noise, it's the echo of creation itself. It connects us to a time long before stars, planets, or life existed, offering a humbling glimpse into the universe's origins. And as we continue to study this ancient light, we uncover not just the story of how the universe began, but also the forces that continue to shape it today. The cosmic microwave background is more than just an afterglow. It's a window into the deepest mysteries of existence. Now, let's dive into one of the most groundbreaking discoveries in modern physics: gravitational waves. Imagine the fabric of spacetime as a calm, undisturbed pond. Now, picture dropping a massive boulder into that pond. The impact sends ripples radiating outward, distorting the water's surface. Gravitational waves are the cosmic equivalent of those ripples, but instead of water, they travel through the very fabric of spacetime itself. These waves are caused by some of the most violent and energetic events in the universe: colliding black holes, merging neutron stars, and even the explosive birth of the cosmos during the Big Bang. The story of gravitational waves begins over a century ago with Albert Einstein's theory of general relativity. In 1915, Einstein proposed that massive objects, like stars or black holes, could warp spacetime around them. He also predicted that when these objects moved or collided, they would send ripples through spacetime gravitational waves. For decades, this idea remained just that, a prediction. Detecting these waves seemed almost impossible. They are incredibly faint, requiring instruments sensitive enough to measure distortions smaller than 1,000th the width of a proton. It wasn't until 2015 that scientists finally succeeded, using an extraordinary instrument called LIGO, the Laser Interferometer Gravitational Wave Observatory. The first detection was a historic moment. LIGO observed the ripples from two black holes colliding over 1 billion light-years away. The event released more energy in a fraction of a second than all the stars in the observable universe combined. The discovery not only confirmed Einstein's century-old prediction, but also opened an entirely new way to explore the cosmos. Before gravitational waves, astronomers relied almost entirely on light, visible, infrared, X-rays, and radio waves to study the universe. But gravitational waves are different. They allow us to hear the universe, picking up vibrations from events that don't emit light, like black hole mergers. What makes gravitational wave astronomy so revolutionary is its ability to reveal the invisible. Traditional telescopes can't see black holes, but gravitational waves can. They can detect the moment two black holes spiral into each other, the violent collision of neutron stars, or even the faint echoes of the Big Bang itself. It's like having a new sense, one that lets us perceive the universe in ways we never could before, and the discoveries keep coming. Since that first detection, LIGO and its counterpart, Virgo, have observed dozens of gravitational wave events, each one offering new insights into the cosmos. One of the most remarkable discoveries came in 2017, when LIGO and Virgo detected ripples from two neutron stars colliding. This event wasn't just observed through gravitational waves, it was also seen by telescopes across the electromagnetic spectrum. The collision created a spectacular light show, known as a kilonova, and produced heavy elements like gold and platinum. It was a perfect example of how gravitational waves and traditional astronomy can work together, painting a fuller picture of the universe's most dramatic events. Gravitational waves are more than just scientific curiosities, they're transforming our understanding of the cosmos. They've given us a new tool to test the limits of Einstein's theory, explore the nature of black holes, and even probe the early universe. Every time we detect a new wave, it's like tuning in to a cosmic symphony, one that tells the story of the universe's most violent and awe-inspiring events. And as our detectors become more sensitive, who knows what other secrets these ripples in space-time will reveal? The universe is full of surprises, and gravitational waves are helping us uncover them, one ripple at a time. Now, let's journey beyond our solar system to a realm of endless possibilities: exoplanets. These are worlds that orbit stars other than our sun, and they come in an astonishing variety. Picture a galaxy not just filled with stars, but with billions of planets, each with its own unique story. Some are rocky, like Earth, while others are gas giants, dwarfing even Jupiter. And then there are those that lie in the so-called habitable zone, where conditions might be just right for liquid water, and perhaps even life. The discovery of exoplanets is one of the most exciting chapters in modern astronomy. It wasn't until 1992 that the first confirmed exoplanet was found, orbiting a pulsar over 2,000 light-years away. Since then, the pace of discovery has been breathtaking. Thanks to missions like NASA Kepler and TESS, scientists have identified thousands of these distant worlds, each one expanding our understanding of what's possible in the cosmos. What's truly remarkable is the diversity we've uncovered. There are planets with years shorter than a week, planets so close to their stars that their surfaces are molten, and even planets that orbit two stars at once, like the fictional Tatooine from Star Wars. But what really captures our imagination are the Earth-like exoplanets, those that might resemble our own world. These are planets with solid surfaces, orbiting within their star's habitable zone, where temperatures could allow for liquid water. One of the most famous is Proxima Centauri b, located just over 4 light-years away. While we don't yet know if it has an atmosphere or oceans, its proximity makes it a prime target for future exploration. Then there's the TRAPPIST-1 system, a collection of 7 Earth-sized planets, 3 of which lie in the habitable zone. Could one of these worlds host life? It's a tantalizing question that drives much of the research in this field. The search for exoplanets isn't just about finding new worlds, it's about understanding our place in the universe. Every discovery tells us something about how planets form, how common Earth-like conditions might be, and whether life could exist elsewhere. And the methods we use to find these planets are as fascinating as the discoveries themselves. One technique, called the transit method, involves measuring the tiny dip in a star's brightness as a planet passes in front of it. Another, the radial velocity method, detects the slight wobble of a star caused by the gravitational pull of an orbiting planet. These tools, combined with advancements in telescope technology, have turned exoplanet hunting into one of the most dynamic fields in astronomy. But the ultimate goal goes beyond cataloging distant worlds. It's about answering one of humanity's oldest questions: are we alone? While we haven't found definitive evidence of extraterrestrial life yet, the sheer number of exoplanets and the variety of environments they offer suggests that the possibilities are vast. Some scientists believe that life could exist in unexpected places, like the icy moons of gas giants or even rogue planets that drift through space without a star. The universe, it seems, is far more creative than we ever imagined. Exoplanets remind us that our solar system is just one small part of a much larger cosmic tapestry. They challenge us to think beyond our own backyard and imagine what might lie in the uncharted reaches of the galaxy. And as we continue to explore these distant worlds, we're not just uncovering the secrets of the universe, we're also learning more about ourselves. Every new discovery brings us closer to understanding the grand story of existence and perhaps finding our place within it. Now, let's turn our attention to one of the most breathtaking and essential phenomena in the cosmos: nebulae. These colossal clouds of gas and dust are more than just stunning celestial landscapes. They are the cradles of stars, the factories where the universe crafts its luminous jewels. Imagine a vast, glowing nursery where the raw ingredients of stars swirl in intricate patterns, lit by the faint glow of infant suns just beginning to shine. This is the world of nebulae, where the cycle of stellar life begins anew. Nebulae come in an astonishing variety, each with its own unique characteristics and beauty. Emission nebulae, for example, are like cosmic lanterns, glowing brightly as they absorb energy from nearby stars. The iconic Orion Nebula, visible even to the naked eye, is one such example, a vibrant tapestry of gas and light where new stars are being born. Then there are reflection nebulae, which don't emit their own light but instead reflect the light of nearby stars, creating a softer, almost ethereal glow. And let's not forget dark nebulae, those shadowy clouds that block the light behind them, carving out stark silhouettes against the starry backdrop. These enigmatic structures remind us that even in the void of space, darkness plays a vital role in shaping the cosmos. But nebulae aren't just beautiful to look at, they're also fundamental to the life cycle of stars. When a massive star reaches the end of its life and explodes in a supernova, it scatters its remains across space. These remnants, gas, dust, and heavier elements mix with the surrounding interstellar medium, forming the building blocks of new nebulae. Over millions of years, gravity pulls these materials together, compressing them until they ignite into new stars. It's a cosmic recycling program on a grand scale, where the death of one star fuels the birth of countless others. In this way, nebulae are not just the birthplaces of stars, they are the threads that connect generations of stellar life. The process of star formation within a nebula is as intricate as it is awe-inspiring. Dense pockets of gas and dust, known as molecular clouds, collapse under their own gravity, heating up as they become more compact. Eventually, the pressure and temperature at the core become so intense that nuclear fusion ignites and a star is born. Surrounding material may coalesce into planets, moons, and asteroids, creating entire solar systems. It's a reminder that every star, every planet, and every speck of dust in the universe has its origins in these cosmic clouds. What makes nebulae even more fascinating is their role in shaping the chemical makeup of the universe. The heavier elements forged in the hearts of stars, carbon, oxygen, iron, and more, are scattered into space when those stars die. These elements become part of the nebulae that give rise to new stars and planets. In a very real sense, the atoms that make up your body were once part of a nebula, billions of years ago. It's a profound connection that ties us to the cosmos, reminding us that we are all made of star stuff. Nebulae are also some of the most photographed objects in the night sky, their vibrant colors and intricate shapes captivating both astronomers and casual stargazers alike. Thanks to advanced telescopes and imaging techniques, we can now see these cosmic clouds in unprecedented detail, revealing their complex structures and the processes taking place within them. Each image tells a story of creation, destruction, and the endless cycle of stellar life. As we gaze at these celestial wonders, we're reminded of the universe's boundless creativity and resilience. Nebulae are not just static clouds, they are dynamic, ever-changing environments where the drama of cosmic evolution unfolds. They challenge us to think beyond our own world and imagine the vast processes that have shaped, and continue to shape, the cosmos. And in their swirling gas and dust, we find not just the birthplaces of stars, but also a deeper understanding of our own origins and the intricate web of life that connects us to the universe. From the vibrant birth of stars in nebulae to the explosive brilliance of supernova, the life cycle of a star is a cosmic drama unlike any other. But what happens when a star like our Sun reaches the end of its journey? It doesn't explode in a fiery supernova or collapse into a black hole. Instead, it transforms into something far more subtle yet equally fascinating, a white dwarf. These stellar remnants are the quiet endgame for stars like our own, and they hold secrets that illuminate the ultimate fate of most stars in the universe. A white dwarf is what remains after a star has burned through its nuclear fuel. Picture a star like the Sun, shining steadily for billions of years, fusing hydrogen into helium in its core. Eventually, it exhausts its fuel, shedding its outer layers in a shimmering display known as a planetary nebula. What's left is a dense, Earth-sized core, packing half the mass of the original star into a tiny volume. To put it another way, imagine compressing the Sun into a sphere no larger than our planet. The result is a white dwarf, a celestial object so dense that a single teaspoon of its material would weigh as much as an elephant. But don't let their small size fool you. White dwarfs are incredibly hot, with surface temperatures reaching up to 100,000 degrees Celsius. They glow faintly, not from nuclear fusion, but from the residual heat left over from their stellar lives. Over billions of years, they slowly cool and fade, eventually becoming dark, cold objects known as black dwarfs. However, the universe isn't old enough for any black dwarfs to exist yet, a reminder of just how long these stellar embers can linger. What makes white dwarfs truly remarkable is their role in some of the most spectacular events in the cosmos. In certain binary star systems, a white dwarf can pull material from its companion star. As it accumulates matter, the pressure and temperature at its core rise. If it reaches a critical threshold, the white dwarf can reignite in a cataclysmic explosion known as a Type Ia supernova. These explosions are so consistent in brightness that astronomers use them as standard candles to measure vast cosmic distances. They've been instrumental in mapping the expansion of the universe and even led to the discovery of dark energy. Studying white dwarfs also gives us a glimpse into the future of our own sun. In about 5 billion years, after swelling into a red giant and shedding its outer layers, the sun will leave behind a white dwarf. This dense core will be all that remains of our star, slowly cooling over trillions of years. It's a humbling thought that even the sun, the anchor of our solar system, will one day fade into a faint cosmic ember. Yet, white dwarfs are more than just stellar tombstones. They're natural laboratories for testing the laws of physics under extreme conditions. Their intense gravity creates environments where matter behaves in strange and unpredictable ways. For instance, the electrons in a white dwarf are packed so tightly that they form a quantum state known as degenerate matter. This exotic material defies ordinary physics, offering scientists a unique opportunity to explore the boundaries of our understanding. White dwarfs also play a crucial role in enriching the universe. The material they shed before becoming white dwarfs, through planetary nebulae or supernova, contains heavy elements like carbon, nitrogen, and oxygen. These elements are scattered across the cosmos, becoming the building blocks for new stars, planets, and even life. In a way, white dwarfs are silent contributors to the ongoing story of the universe, ensuring that the cycle of stellar life continues. As we study these dense, fading remnants, we're reminded of the delicate balance that governs the lives of stars. White dwarfs may not shine as brightly as their younger counterparts, but they hold a quiet power, offering us a window into the past, present, and future of the cosmos. They are a testament to the enduring legacy of stars, and a reminder that even in their twilight, they continue to shape the universe in ways we are only beginning to understand. If neutron stars are the universe's cosmic powerhouses, then magnetars are their volatile, hypermagnetic cousins. These extraordinary objects are a rare breed of neutron stars, but with one jaw-dropping twist, they possess magnetic fields so strong they defy imagination. To put it into perspective, a magnetar's magnetic field is a quadrillion times more powerful than Earth's. To give you an idea of just how intense that is, if a magnetar were located halfway across the galaxy, tens of thousands of light years away, its magnetic field could still wipe the data off your credit card. It's a level of magnetism so extreme it feels almost like science fiction, yet it's very real. So, how do these cosmic power-ups come to exist? Magnetars are born from the ashes of massive stars that have gone supernova. When a star collapses, its core can form a neutron star, but under certain conditions, like having an unusually strong magnetic field to begin with, it can become a magnetar. These conditions are rare, which is why magnetars are so uncommon. Out of the billions of neutron stars in the Milky Way, only a few dozen have been identified as magnetars. But what they lack in numbers, they make up for in sheer ferocity. The magnetic fields of magnetars are so intense that they can literally twist and distort the fabric of space itself. This leads to some of the most violent and energetic phenomena in the universe. When a magnetar's magnetic field undergoes a sudden rearrangement, a process known as a starquake, it releases an enormous amount of energy in the form of X-rays and gamma rays. These bursts are so powerful they can be detected across the universe, even affecting Earth's upper atmosphere. In 2004, A magnetar eruption was so intense it temporarily ionized Earth's ionosphere, disrupting radio communications and even triggering safety protocols on satellites. It's a stark reminder of how interconnected we are with the cosmos, even from such a vast distance. But what makes magnetars truly fascinating is their ability to serve as natural laboratories for studying extreme physics. Their magnetic fields are so strong that they alter the behavior of matter in ways we can't replicate on Earth. For example, in a magnetar's magnetic field, atoms are stretched into long, thin shapes, and even the vacuum of space itself is thought to behave differently. These conditions allow scientists to test theories about the fundamental nature of matter, energy, and even space-time. Magnetars are like cosmic particle accelerators, pushing the boundaries of what we know about the universe. Despite their destructive potential, magnetars also offer a glimpse into the delicate balance that governs the cosmos. Their magnetic fields are so powerful they can actually slow down the star's rotation over time, a phenomenon known as magnetic braking. This process releases energy, heating the magnetar's surface and creating a glowing corona of X-rays. It's a reminder that even the most extreme objects in the universe are subject to the same physical laws that shape everything else, just on a much grander scale. Magnetars are a testament to the universe's capacity for extremes. They challenge our understanding of physics, push the limits of what we thought was possible, and remind us that the cosmos is full of surprises. Whether it's their ability to warp space, produce bursts of energy that ripple across galaxies, or serve as cosmic laboratories, magnetars are a fascinating window into the most intense magnetic environments in existence. And as we continue to study these magnetic marvels, we uncover not just the secrets of magnetars, but also the forces that shape the universe itself. While the universe is often imagined as a bustling expanse filled with stars, galaxies, and nebulae, there's another side to the cosmic story, one defined by emptiness. Enter cosmic voids, the sprawling, almost ghostly regions of space where galaxies are few and far between. These voids are not just random gaps, they are colossal structures in their own right, some stretching hundreds of millions of light-years across. To visualize them, picture the universe not as a uniform sea of stars, but as a sponge, a web of galaxy clusters, filaments, and walls, with vast, empty spaces in between. These are the cosmic voids, and they hold secrets that challenge our understanding of the cosmos. What makes cosmic voids so fascinating is their sheer scale and the role they play in the universe's architecture. While galaxies tend to cluster together, forming dense regions of matter, voids are the opposite, expansive regions where matter is sparse, and the density of galaxies is exceptionally low. This isn't just a random occurrence, it's a direct result of the universe's evolution. In the early universe, tiny fluctuations in density led to the formation of galaxies and galaxy clusters in some areas, while others were left relatively empty. Over billions of years, gravity pulled matter into the denser regions, leaving behind these vast, empty voids. But don't let their emptiness fool you. These voids are far from insignificant. Cosmic voids are more than just empty space. They are dynamic regions that influence the universe on the largest scales. One of their most profound roles is in the expansion of the universe itself. As dark energy drives galaxies apart, it does so more effectively in voids, where the gravitational pull of matter is weaker. This means that voids are not just passive bystanders in the cosmic dance, they are active participants, shaping the rate at which the universe expands. In a way, they act as cosmic accelerators, stretching the fabric of spacetime in ways that challenge our understanding of gravity and dark energy. But how do we study something that's, quite literally, defined by its absence? Scientists use a combination of observations and simulations to map these voids. By studying the distribution of galaxies, astronomers can identify the boundaries of voids and measure their size. These observations reveal a universe that's far more structured than it might appear at first glance, a cosmic web where galaxies are the threads and voids are the spaces in between. This intricate structure helps us understand not just the universe's present state, but also its past and future. One of the most intriguing aspects of cosmic voids is their potential to test our theories about the universe. Because they contain so little matter, they offer a unique environment to study the effects of dark energy and the nature of gravity on large scales. For example, light traveling through a void can be subtly distorted, a phenomenon known as the integrated Sachs-Wolf effect. This distortion provides clues about the properties of dark energy and the overall geometry of the universe. In this way, voids act as natural laboratories, allowing us to probe the most fundamental questions in cosmology. Cosmic voids also remind us of the universe's complexity and balance. While galaxies and galaxy clusters are the stars of the cosmic show, voids are the quiet, often overlooked backdrop that makes the entire structure possible. They highlight the delicate interplay between matter, gravity, and dark energy, a dance that has been ongoing since the dawn of time. And as we continue to explore these vast, empty regions, we gain a deeper appreciation for the universe's intricate design and the forces that shape it. In the end, cosmic voids are a testament to the universe's diversity. They challenge us to look beyond the bright lights of galaxies and stars and consider the emptiness that surrounds them. They remind us that even in a universe filled with wonders, sometimes the most profound mysteries lie in the spaces between. And as we unravel their secrets, we come closer to understanding not just the voids themselves, but the grand, interconnected story of the cosmos. Now, let's shift our focus to one of the most thrilling phenomena in the cosmos: hypervelocity stars. These aren't your average stars leisurely orbiting the center of the galaxy. No, hypervelocity stars are the ultimate cosmic fugitives, hurtling through space at breakneck speeds, so fast they can escape the Milky Way entirely. Imagine a star not just drifting, but being flung out of the galaxy like a slingshot projectile, racing through the void at millions of miles per hour. These are the runaways of the galaxy, and their story is as dramatic as it is mysterious. So, how do these stars get kicked out of the galaxy in the first place? The answer lies in the heart of the Milky Way, where a supermassive black hole lurks. When a star wanders too close to this gravitational titan, it can be caught in a deadly dance. If there's a binary star system, two stars orbiting each other, things get even more intense. The black hole's immense gravity can tear the pair apart, capturing one star while flinging the other outward at incredible speeds. It's a cosmic game of gravitational pinball, and the ejected star becomes a hypervelocity star, destined to roam the intergalactic wilderness. But hypervelocity stars aren't just cosmic curiosities, they're also invaluable tools for astronomers. Their trajectories tell us a lot about the environment that launched them. By studying their paths, scientists can learn about the Milky Way's central black hole, its mass, and even the history of stellar interactions near the galactic core. It's like finding a speeding bullet and tracing it back to the gun that fired it. Each hypervelocity star carries a story encoded in its motion, and decoding that story helps us piece together the dynamics of our galaxy. What's even more fascinating is where these stars end up. Once they're ejected, they don't just drift aimlessly. They travel through the vast, empty regions between galaxies, becoming interstellar nomads. Some may eventually encounter another galaxy, while others will drift forever in the darkness of intergalactic space. It's a lonely existence, but one that offers a unique perspective on the universe. These stars are like cosmic messengers, carrying information from the heart of the Milky Way to the farthest reaches of the cosmos. Hypervelocity stars also challenge our understanding of stellar evolution. Most stars live out their lives in the relative calm of their home galaxies, but these speedsters are thrust into an entirely different environment. How does the journey affect them? Do they age differently? Could they even harbor planets despite their extreme speeds? These are questions that keep astronomers intrigued as they study these stellar outliers to uncover the secrets of their survival. In a universe filled with wonders, hypervelocity stars stand out as a testament to the raw power of gravity and the intricate interplay of cosmic forces. They remind us that even in the seemingly orderly structure of a galaxy, chaos and drama are never far away, and as we continue to track these stellar speedsters, we gain not just insights into their origins, but also a deeper appreciation for the dynamic, ever-changing nature of the cosmos. They are the rebels of the galaxy, racing through the void, and their story is one of power, escape, and the eternal quest for freedom. Deep in the cosmos, beyond the familiar constellations and the glittering expanse of the Milky Way, lies a mystery that has puzzled scientists for decades: the Great Attractor. This enigmatic force, hidden behind the veil of our galaxy's dust and stars, exerts a gravitational pull so powerful it's dragging entire galaxies, including our own, toward it. Imagine the universe as a vast river, with galaxies like leaves drifting on its surface. Now, picture an invisible current pulling all those leaves toward a single point. That's the Great Attractor, a cosmic anomaly that defies explanation and challenges everything we know about the universe's large-scale structure. Located in the direction of the Centaurus constellation, the Great Attractor lies about 250 million light-years from Earth. But here's the catch: it's hidden behind the dense plane of the Milky Way, obscured by interstellar dust and gas. This makes it incredibly difficult to study directly, leaving astronomers to piece together its nature through indirect observations. What we do know is that it exerts an immense gravitational influence, pulling not just our galaxy but hundreds of others in its direction. It's as if the universe has a hidden magnet, and we're all being drawn toward it, whether we like it or not. So, what could the Great Attractor be? One leading theory suggests it's a massive concentration of matter, perhaps a supercluster of galaxies so dense that its gravity dominates the surrounding region. The Norma Cluster, a dense collection of galaxies in the same direction, is thought to be part of this structure, but even this doesn't fully explain the Great Attractor's immense pull. Some scientists speculate that there's something even larger at play, an unseen cosmic structure, or a concentration of dark matter so vast it reshapes the motion of galaxies on a grand scale. Others wonder if it could be connected to even larger structures, like the Shapley supercluster, located even farther away but exerting its own gravitational influence. The Great Attractor isn't just a scientific curiosity, it's a reminder of how much we have yet to discover about the universe. Its existence challenges our understanding of the cosmos's large-scale motion and the forces that shape it. For instance, the Milky Way isn't just drifting aimlessly through space. It's being pulled toward the Great Attractor at a staggering speed of about 600 kilometers per second. And we're not alone. Entire galaxy clusters are being swept along in this cosmic current, creating a vast flow of matter that spans hundreds of millions of light years. It's a humbling thought that even on such an enormous scale, the universe is still full of surprises. Studying the Great Attractor is no easy task. The dust and gas of the Milky Way's plane block much of the light from this region, making it a cosmic blind spot for many telescopes. But advancements in technology, particularly in infrared and radio astronomy, are slowly peeling back the veil. Instruments like the Hubble Space Telescope and ground-based observatories equipped with specialized detectors are helping scientists map the distribution of galaxies and trace the gravitational forces at work. Each new observation brings us closer to understanding this mysterious force and its role in the cosmos. The Great Attractor also raises profound questions about the universe's structure and evolution. Is it a unique anomaly, or are there other great attractors scattered throughout the cosmos? Could it be part of a larger network of gravitational influences that shape the universe on the grandest scales? These questions push the boundaries of cosmology, driving scientists to refine their models and explore new theories. And as we continue to study this cosmic mystery, we're reminded that the universe is far more complex and interconnected than we ever imagined. In the end, the Great Attractor is more than just a hidden force in the cosmos. It's a symbol of the universe's endless mysteries. It challenges us to look beyond what we can see, to question our assumptions, and to embrace the unknown. And as we unravel its secrets, we gain not just a deeper understanding of the universe's structure, but also a greater appreciation for the forces that shape our place within it. The Great Attractor may be pulling us toward it, but it's also pulling us closer to the truth. Beyond the familiar planets and asteroids, far past the orbit of Neptune, lies a realm so distant it feels almost mythical, the Ouit Cloud. This vast, spherical shell of icy objects surrounds our solar system like a cosmic moat, stretching nearly a light year from the Sun. To grasp its scale, imagine this. If the solar system were the size of a football field, the Ouit Cloud would extend miles beyond the stadium. It's a place where the sun's light is faint and temperatures hover just above absolute zero, a frozen frontier that holds the keys to some of the solar system's deepest secrets. The Ouit Cloud is often described as a reservoir of comets, and for good reason. It's home to trillions of icy bodies, remnants from the solar system's earliest days. These objects, some as small as a pebble and others as large as mountains, are made of pristine material untouched by the heat and activity of the inner solar system. Occasionally, the gravitational tug of a passing star or the collective pull of the Milky Way's disk nudges one of these icy bodies out of its orbit, sending it hurtling toward the sun. When that happens, we witness the birth of a long-period comet, a dazzling visitor that can take thousands or even millions of years to complete a single orbit. But the Ouit Cloud isn't just a cosmic storage locker for comets, it's a time capsule. The icy bodies it holds are relics from 4-6 billion years ago, when the solar system was just a swirling disk of gas and dust. By studying these ancient objects, scientists can piece together the conditions that existed during the solar system's formation. What was the chemical makeup of the primordial cloud that birthed the sun and planets? How did the building blocks of life, like water and organic molecules, make their way to Earth? The answers to these questions may lie hidden in the icy depths of the Ouit Cloud. Despite its importance, the Ouit Cloud remains one of the most challenging regions to study. Its distance is so vast that even our most advanced spacecraft would take tens of thousands of years to reach it. Instead, astronomers rely on indirect methods, like observing the trajectories of long-period comets, to infer its structure and composition. Every comet that enters the inner solar system is like a messenger, carrying clues about the Ouit Cloud's origins and history. These icy travelers provide a rare glimpse into the outer reaches of our cosmic neighborhood, offering insights that ground-based telescopes simply can't match. The Ouit Cloud also raises fascinating questions about the solar system's boundaries. Where does our cosmic neighborhood end, and where does interstellar space begin? The Ouit Cloud marks the edge of the Sun's gravitational influence, a place where the pull of other stars begins to take over. It's a reminder that even our solar system isn't an isolated island in space. It's part of a broader galactic ecosystem, connected to the stars around us in ways we're only beginning to understand. As we continue to explore this distant frontier, we're reminded of how much we still have to learn about our own cosmic backyard. The Ouit Cloud is a testament to the solar system's complexity and the enduring mysteries that lie just beyond our reach. It challenges us to think bigger, to look deeper, and to imagine the vastness of space not as an empty void, but as a treasure trove of ancient secrets waiting to be uncovered. And as we piece together its story, we come closer to understanding not just the origins of comets, but the very beginnings of our solar system itself. Now, let's tackle one of the most perplexing mysteries in the cosmos, the Fermi Paradox. Picture this: the universe is unimaginably vast, with hundreds of billions of galaxies, each containing hundreds of billions of stars. Statistically, the odds of life emerging elsewhere seem almost certain, and yet, despite this cosmic abundance, we haven't found a single trace of extraterrestrial intelligence. The question is simple but profound: where is everyone? This is the heart of the Fermi Paradox, a puzzle that has baffled scientists and dreamers alike for decades. The paradox gets its name from physicist Enrico Fermi, who famously posed the question during a casual conversation in 1950. If the universe is so old and so vast, he reasoned, why haven't we encountered any evidence of alien civilizations? After all, even at sublight speeds, a technologically advanced species should have had enough time to colonize the galaxy by now. The silence is deafening, and it forces us to confront some uncomfortable possibilities. Are we truly alone, or is there something we're missing? One of the most compelling explanations is what's known as the rare Earth hypothesis. This idea suggests that while the universe may be teeming with planets, the specific conditions required for complex life, let alone intelligent civilizations, are exceedingly rare. Earth's unique combination of factors, from its stable orbit and protective magnetic field to the presence of liquid water and a large moon, might be far more exceptional than we realize. If this is true, then the emergence of intelligent life could be a cosmic fluke, a one-in-a-trillion event that hasn't happened elsewhere, or at least not yet. But what if life isn't rare? What if intelligent civilizations are out there, but they're simply too far away or too different for us to detect? This is where the concept of the Great Filter comes into play. The Great Filter is a hypothetical barrier that prevents life from advancing to the point of interstellar communication or colonization. It could exist at any stage of development. Perhaps life rarely evolves beyond single-celled organisms, or maybe advanced civilizations inevitably destroy themselves through war, environmental collapse, or technological catastrophe. If this is the case, the silence we hear might be a warning, a sign that the universe is littered with the ruins of civilizations that couldn't overcome their own challenges. Then there's the possibility that we're looking for extraterrestrial life in the wrong way. Our current methods of searching, scanning the skies for radio signals, or looking for biosignatures in exoplanet atmospheres, are based on assumptions about how alien civilizations might behave. But what if they're using technologies or communication methods we can't even imagine? Or what if they're deliberately avoiding contact, choosing to remain hidden for reasons we can't yet fathom? The universe is full of possibilities, and our understanding is still in its infancy. The Fermi Paradox isn't just a scientific curiosity, it's a mirror that reflects our deepest questions about existence. Are we unique? Are we alone? Or are we simply at the very beginning of a journey that will one day connect us with others across the stars? For now, the silence remains, a haunting reminder of how much we still have to learn. But it's also an invitation to keep searching, to keep questioning, and to remain open to the infinite possibilities that the cosmos holds. The answer to the Fermi Paradox might not just reveal the nature of extraterrestrial life, it might also tell us something profound about ourselves. Now, let's venture into one of the most mind-bending concepts in modern cosmology, the multiverse. Imagine our universe not as a singular, isolated entity, but as one bubble in an endless cosmic foam, each bubble representing a completely separate universe with its own unique set of physical laws. This is the essence of the multiverse theory, a radical idea that suggests our reality is just one of countless others, each existing in its own pocket of spacetime. It's a concept that stretches the limits of our imagination and challenges everything we thought we knew about existence. The multiverse isn't just a wild idea plucked from science fiction. It's grounded in some of the most advanced theories in physics. One of the key frameworks supporting this idea is cosmic inflation, the theory that our universe underwent a rapid expansion just moments after the Big Bang. According to this model, inflation didn't just happen once. It could be an ongoing process, continuously giving rise to new universes in an ever-expanding cosmic landscape. Each of these universes would have its own distinct properties, from the strength of gravity to the number of dimensions. It's like a cosmic lottery, with every universe spinning a different set of physical rules. String theory, another cornerstone of modern physics, also lends weight to the multiverse concept. This theory proposes that the fundamental building blocks of the universe are tiny, vibrating strings, and the way they vibrate determines the properties of particles and forces. But string theory doesn't predict just one universe. It suggests a staggering number of possible configurations, each corresponding to a different universe with its own unique laws of physics. In this view, the multiverse isn't just a speculative idea, it's a natural outcome of the mathematics behind our deepest theories. One of the most intriguing implications of the multiverse is its potential to explain the fine-tuning of our universe. Why do the fundamental constants like the strength of gravity or the mass of an electron have values that allow for the existence of stars, planets, and life? If there are countless universes, each with different constants, it's no surprise that one of them would have the right conditions for life to emerge. In this context, our universe isn't special, it's just one of many, and we happen to be in the one where life is possible. It's a humbling thought, but also a profoundly liberating one. Yet, the multiverse isn't without its challenges, because these other universes, by definition, lie beyond our observable horizon. We have no direct way to test their existence. This has led some to argue that the multiverse is more philosophy than science, a fascinating idea, but one that may forever remain untestable. Others, however, see it as a natural extension of our most successful theories, a framework that could one day help us unlock deeper truths about reality. The multiverse also raises profound questions about the nature of existence. If there are infinite universes, does that mean there's a version of you living in every possible scenario? Could there be universes where the laws of physics are so alien that life, as we know it, is impossible? These questions push the boundaries of what we consider real and challenge us to think beyond the confines of our own universe. It's a reminder that the cosmos is far stranger and more complex than we can possibly imagine. As we explore the multiverse, we're not just expanding our understanding of the universe, we're redefining what it means to exist. It's a journey that takes us from the smallest scales of quantum mechanics to the vast, unexplored reaches of cosmic infinity. And while the multiverse remains a speculative idea, it's one that inspires us to keep asking the biggest questions. What is reality? Are we alone? And what lies beyond the edges of our universe? In the end, the multiverse isn't just a theory, it's an invitation to dream bigger, to imagine a cosmos without limits, and to embrace the infinite possibilities that lie beyond the stars. As we peer into the distant future of the cosmos, one question looms larger than all others. How will it all end? Among the many possibilities, one stands out as both dramatic and deeply poetic: the Big Crunch. Picture this: after billions of years of expansion, the universe's growth slows, stops, and then begins to reverse. Galaxies, once drifting apart, start to converge. Space itself shrinks, collapsing inward until everything — stars, planets, even the fabric of spacetime — is crushed into a single, infinitely dense point. It's a cosmic do-over, a return to the singularity from which the universe began. This is the Big Crunch, a hypothetical ending that challenges our understanding of time, space, and existence itself. The Big Crunch isn't just a fascinating thought experiment. It's a scenario rooted in the delicate balance between two of the universe's most fundamental forces: gravity and dark energy. Gravity, the force that pulls matter together, has been the dominant player in the cosmos for most of its history. Dark energy, on the other hand, is the mysterious force driving the universe's accelerated expansion. The fate of the universe hinges on which of these forces wins out in the end. If gravity eventually overcomes dark energy, the universe's expansion will slow, halt, and reverse, leading to the Big Crunch. But if dark energy maintains its dominance, the universe will continue to expand forever, cooling into a cold, dark void, a scenario known as the Big Freeze. What makes the Big Crunch so compelling is its cyclical nature. In this scenario, the universe doesn't just end, it resets. The collapse into a singularity could trigger another Big Bang, birthing a new universe from the ashes of the old. It's a cosmic cycle of birth, death, and rebirth, echoing ancient myths and philosophies about the eternal return. For some, this idea is comforting, suggesting that even in the face of ultimate destruction, there's the promise of renewal. For others, it's a stark reminder of the universe's impermanence, a humbling thought that even the grandest structures in existence are subject to the same forces of change. But how likely is the Big Crunch? The answer lies in the universe's density. If the total amount of matter and energy in the cosmos is high enough, gravity could eventually overcome dark energy's push, leading to the collapse. However, current observations suggest that dark energy is winning the cosmic tug of war, making the Big Crunch seem less probable. Still, the universe is full of surprises, and our understanding of dark energy is far from complete. What we know today could be upended by tomorrow's discoveries, leaving the door open for this dramatic ending. The Big Crunch also raises profound questions about the nature of time and space. If the universe collapses, does time itself reverse? Would the laws of physics change as space shrinks? These are questions that push the boundaries of our knowledge, challenging us to think beyond the familiar and explore the limits of what's possible. It's a reminder that the universe isn't just a static backdrop to our lives. It's a dynamic, ever-changing entity, full of mysteries waiting to be unraveled. Exploring the Big Crunch isn't just about understanding the universe's end, it's about appreciating its journey. Whether the cosmos collapses into a singularity or expands into a cold, dark void, the story of the universe is one of constant transformation. Each scenario offers a unique perspective on the forces that shape existence, from the tiniest particles to the largest structures in the cosmos. And as we ponder these possibilities, we're reminded of our place in the grand tapestry of time and space, a fleeting moment in an infinite story, yet one filled with the wonder of discovery and the thrill of the unknown. The Big Crunch may be one of many possible endings, but it's also a beginning, a starting point for new questions, new theories, and new ways of seeing the universe we call home. Now, let's turn to a chilling possibility, one that paints a starkly different picture of the universe's future than the fiery collapse of the Big Crunch. This is the Big Freeze, also known as the heat death of the universe, a scenario where the cosmos doesn't collapse but instead expands forever, cooling into an endless, lifeless void. Imagine a universe where the last stars flicker out, galaxies drift so far apart they can no longer see one another, and all activity grinds to a halt. It's not a dramatic explosion or a sudden collapse, but a slow, inexorable fade into darkness, a cosmic winter that stretches on for eternity. At the heart of this scenario is dark energy, the mysterious force driving the universe's accelerated expansion. Unlike gravity, which pulls matter together, dark energy pushes it apart, acting as a kind of cosmic repellent. Over billions of years, this force will continue to stretch the fabric of spacetime, scattering galaxies like leaves in a cosmic wind. Stars will exhaust their fuel, black holes will evaporate, and eventually, even the smallest particles will decay. The universe will become a cold, empty expanse, where temperatures approach absolute zero, and all forms of energy are evenly distributed. It's a fate devoid of heat, light, or life, a silent, static end to everything we know. What makes the Big Freeze so haunting is its inevitability, at least based on our current understanding of the cosmos. Observations of distant supernovae and the cosmic microwave background suggest that dark energy is winning the cosmic tug of war, driving the universe toward this cold, desolate future. Unlike the Big Crunch, which offers the possibility of rebirth, the Big Freeze represents a final, irreversible end. It's a reminder that even the most vibrant and dynamic systems are subject to entropy, the natural tendency toward disorder and equilibrium. In this scenario, the universe doesn't just die, it fades away, leaving behind a cold, featureless void. But the Big Freeze isn't just a bleak vision of the future. It's also a profound challenge to our understanding of time and existence. If the universe continues to expand indefinitely, what happens to time itself? Will it slow to a crawl or even stop altogether? These questions push the boundaries of physics and philosophy, forcing us to grapple with concepts that defy intuition. The Big Freeze forces us to confront the idea that even time, something we consider absolute and unchanging, may have an end, and then there's the question of life. In a universe destined for the Big Freeze, what happens to the civilizations that might exist billions of years from now? Could they adapt to the changing conditions, finding ways to survive in a universe that grows colder and darker with each passing eon? Or are they, like us, destined to be mere flickers in the cosmic night, brief sparks of consciousness in an otherwise silent and empty cosmos? These are questions that bridge the gap between science and humanity, reminding us that the fate of the universe is deeply intertwined with our own. The Big Freeze also serves as a humbling reminder of the universe's scale and impermanence. We live in a fleeting moment of cosmic history, a time when stars still shine, galaxies still collide, and life still thrives. But the universe is unimaginably old, and its future stretches far beyond our comprehension. The Big Freeze invites us to think beyond the here and now, to consider the grand sweep of cosmic time and our place within it. It's a perspective that's both sobering and awe-inspiring, a reminder that the universe is far greater and more mysterious than we can ever fully grasp. As we ponder the Big Freeze, we're reminded that the universe's story is still being written. The fate of the cosmos isn't set in stone. It's shaped by the interplay of forces we're only beginning to understand. And while the Big Freeze may seem like a distant and abstract concept, it's also a call to action, a reminder to cherish the time we have, to explore the wonders of the universe, and to seek out the answers to its deepest mysteries. The Big Freeze may be one possible ending, but it's also a beginning, a starting point for new questions, new discoveries, and new ways of understanding the cosmos we call home. Now, let's dive into one of the most intriguing tools in the search for extraterrestrial life, the Drake equation. Think of it as a cosmic calculator, designed not to give us a definitive answer, but to help us frame the question: how many intelligent civilizations might exist in our galaxy? Conceived in 1961 by astronomer Frank Drake, this equation isn't just a mathematical formula, it's a roadmap guiding us through the complexities of estimating the likelihood of life beyond Earth. It's a blend of science and imagination, a way to quantify the unknown and spark curiosity about our place in the universe. At its core, the Drake equation breaks down the vast question of alien civilizations into smaller, more manageable pieces. It starts with the rate at which stars form in the Milky Way, then considers how many of those stars have planets orbiting them. From there, it asks how many of those planets might be in the Goldilocks zone, not too hot, not too cold, but just right for liquid water to exist. These are the building blocks of life as we know it, and the equation invites us to consider each step in the journey from starlight to sentience. But the equation doesn't stop there. It goes on to explore the probability of life emerging on those habitable planets, and whether that life could evolve into intelligent beings capable of communication. It even considers how long such civilizations might last, whether they flourish for millennia or vanish in a cosmic blink. Each factor in the equation is a variable, a piece of the puzzle that scientists are still working to understand. And while the numbers we plug in are often speculative, the equation itself is a powerful tool for organizing our thoughts and guiding our search. What makes the Drake equation so compelling is its ability to balance the known and the unknown. On one hand, it's grounded in solid science. We know, for example, that stars form at a certain rate and that many stars host planets. On the other hand, it forces us to confront the gaps in our knowledge. How common is life? How likely is it to become intelligent? These are questions we're still trying to answer, and the equation reminds us that the search for extraterrestrial life is as much about asking the right questions as it is about finding definitive answers. The Drake equation also highlights the challenges of interstellar communication. Even if intelligent civilizations exist, the vast distances between stars make communication incredibly difficult. A signal sent from a distant planet might take thousands or even millions of years to reach us, and by the time it arrives, the civilization that sent it could be long gone. This raises profound questions about our ability to connect with other beings and whether we're even looking in the right way. Are we listening for radio signals when we should be searching for something else entirely? The equation doesn't provide answers, but it encourages us to think creatively about the possibilities. Despite its speculative nature, the Drake equation has had a lasting impact on astrobiology and the search for extraterrestrial intelligence, or SETI. It's a reminder that science isn't just about what we know, it's about what we're trying to figure out. It's a call to explore, to question, and to imagine. And while we may never know for sure how many civilizations share the galaxy with us, the equation keeps us looking up, wondering, and dreaming of what might be out there. In the end, the Drake equation isn't just a formula, it's a conversation starter. It invites us to think about the universe not as a static place, but as a dynamic, evolving tapestry of possibilities. It challenges us to consider our role in the cosmos and to keep searching for answers, even when the questions seem impossibly big. And as we continue to explore the stars, the Drake equation will remain a guiding light, reminding us that the universe is full of mysteries waiting to be uncovered. Now, let's step into one of the most tantalizing mysteries in the search for extraterrestrial life, a fleeting radio signal that has captivated scientists and dreamers alike for decades. Known as the WOW signal, this brief burst of radio waves, detected in 1977, has become a legendary enigma in the quest to answer the age-old question: are we alone in the universe? Lasting just 72 seconds, the signal was so remarkable that astronomer Jerry Amon, who first spotted it in data from the Big Ear radio telescope, circled the reading in red ink and wrote, "Wow." Next to it, a reaction that gave the signal its iconic name. What made the WOW signal so extraordinary was its intensity and frequency. It originated from a region of space near the constellation Sagittarius and appeared to be a narrowband signal, a hallmark of potential artificial origin. Natural cosmic phenomena, like pulsars or quasars, typically emit broad-spectrum signals, but the WOW signal was different. It was focused, powerful, and unlike anything astronomers had ever encountered. For a brief moment, it seemed like we might have stumbled upon evidence of intelligent life beyond Earth, but as quickly as it appeared, the signal vanished, leaving behind more questions than answers. Theories about the WOW signal's origin have sparked endless debate. Some scientists argue it could have been a message from an extraterrestrial civilization, a deliberate attempt to communicate across the vastness of space. Others suggest it might have been the result of a natural but rare cosmic event, such as a comet or an interstellar cloud passing through the telescope's line of sight. However, no definitive explanation has ever been found, and despite numerous attempts to detect a repeat signal, the WOW signal remains a one-time occurrence. Its fleeting nature only adds to its mystique, making it one of the most compelling unsolved mysteries in astronomy. What makes the WOW signal so fascinating isn't just its potential implications, it's the way it challenges us to think about the scale and complexity of the cosmos. If it was indeed a message from an alien civilization, it would mean that somewhere out there, intelligent beings were reaching out, even if only for a moment. But if it was a natural phenomenon, it underscores how much we still have to learn about the universe's hidden mechanisms. Either way, the WOW signal serves as a reminder of how vast and mysterious the cosmos truly is. The search for extraterrestrial intelligence, or SETI, has come a long way since 1977, with advanced telescopes and algorithms now scanning the skies for signals that might hint at alien life. Yet, the WOW signal remains a landmark in this ongoing quest. It's a reminder that the universe is full of surprises, and that even the briefest flicker of something unusual can ignite our curiosity and imagination. Whether it was a cosmic hello or just a fleeting glitch, the WOW signal continues to inspire us to keep looking, listening, and wondering what else might be out there. As we reflect on this mysterious signal, we're reminded that the search for extraterrestrial life is as much about patience and persistence as it is about technology and discovery. The WOW signal may have been a fleeting moment, but its impact has been enduring, sparking decades of curiosity and debate. It's a testament to the power of the unknown and a call to keep exploring the vast, uncharted reaches of the cosmos. After all, the next signal or the next WOW could be just around the corner, waiting for us to tune in. Imagine a civilization capable of harnessing the energy of an entire galaxy, bending stars to their will, constructing megastructures, and traveling across vast cosmic distances as easily as we drive to the grocery store. Sounds like science fiction, right? But what if I told you there's a framework that not only envisions such possibilities, but also helps us understand where humanity stands in the grand scheme of cosmic progress? This is the Kardashev Scale, a visionary tool that ranks civilizations based on their mastery of energy, and it's as thought-provoking as it is humbling. The Kardashev Scale was first proposed in 1964 by Soviet astronomer Nikolai Kardashev, and it's deceptively simple in its design. It categorizes civilizations into three main types: Type I, which can harness all the energy available on their home planet; Type Roman II, capable of controlling the energy output of their entire star; and Type Roman III, which can command the energy of an entire galaxy. Each level represents a leap in technological and societal advancement, so profound it's almost unimaginable. And here's the kicker: humanity isn't even at Type I yet. We're still a Type 0 civilization, relying primarily on fossil fuels and only beginning to tap into renewable energy sources. But that doesn't mean we're not dreaming big. What makes the Kardashev Scale so fascinating is the way it forces us to think about the future, not just for humanity, but for any intelligent life that might exist out there. A Type I civilization, for example, would have mastered renewable energy to the point where they could control weather patterns, prevent natural disasters, and sustain their population indefinitely. They'd have access to unimaginable computing power and the ability to harness every ounce of energy their planet has to offer. Think of it as a world where energy scarcity is a thing of the past, and the focus shifts entirely to exploration, creativity, and growth. But the real mind-benders come when we look at Type Roman II and Type Roman III civilizations. A Type Roman II civilization wouldn't just use solar panels. They might build a Dyson sphere, a megastructure enveloping their star to capture its entire energy output. This isn't just sci-fi speculation. It's a concept grounded in physics, and one that could theoretically allow a civilization to thrive for millions of years. And then there's Type Roman III, a civilization so advanced they could harness the energy of billions of stars, potentially reshaping entire galaxies to suit their needs. The scale doesn't just measure energy consumption, it's a roadmap for what's possible when intelligence and technology reach their zenith. Of course, the Kardashev Scale isn't just about fantasizing about the future. It's also a tool for speculation about extraterrestrial life. If we ever detect signs of a type Roman II or type Roman III civilization, it could revolutionize our understanding of the universe. Imagine discovering a Dyson sphere around a distant star, or detecting energy signatures that suggest a galaxy-spanning network of megastructures. These aren't just hypotheticals, they're potential targets for future astronomical observations, and they highlight the scale's value as a framework for searching for intelligent life. But the Kardashev Scale also serves as a mirror reflecting humanity's potential and our limitations. Right now, we're still grappling with the challenges of a Type 0 civilization, climate change, resource depletion, and the ethical implications of rapid technological advancement. Yet, the scale offers a hopeful vision of what we could achieve if we overcome these hurdles. It challenges us to think beyond short-term problems and consider the long-term trajectory of our species. Could we one day become a Type I civilization? And if so, what would that look like? The answers to these questions could shape the future of humanity itself. The Kardashev Scale isn't just a scientific tool, it's a source of inspiration. It reminds us that the universe is full of possibilities, and that the limits of what we can achieve are defined only by our imagination and ingenuity. Whether we're pondering the capabilities of advanced alien civilizations or dreaming of humanity's future among the stars, the scale invites us to think big, to imagine a cosmos where intelligence and energy mastery go hand in hand. And in doing so, it offers a glimpse of a future where the stars aren't just points of light in the night sky, but stepping stones on the path to greatness. Have you ever stopped to wonder why the universe seems so perfectly suited for life? It's as if every fundamental constant, every physical law, has been meticulously calibrated to allow stars to form, planets to coalesce, and life to emerge. This isn't just a lucky coincidence, it's the heart of the Anthropic Principle, a concept that explores the idea that the universe is fine-tuned for life as we know it. Imagine tweaking just one of these constants, making gravity slightly stronger, or electromagnetism a fraction weaker. The result, a cosmos where stars might never ignite, atoms might never bond, and life as we understand it could never exist. It's a delicate balance, one that raises profound questions about the nature of reality itself. At its core, the Anthropic Principle suggests that the conditions necessary for life aren't random. They're deeply embedded in the fabric of the universe. This idea comes in two main flavors, the weak Anthropic Principle and the strong Anthropic Principle. The weak version simply observes that we exist in a universe capable of supporting life, so it's no surprise we find ourselves here. The strong version takes it a step further, proposing that the universe must have properties that allow life to arise. This stronger interpretation has sparked intense debate, with some suggesting it hints at a deeper, perhaps even intentional, design. But what does it mean for the universe to be fine-tuned? Let's break it down. Take the gravitational constant, for instance. If gravity were just a tiny bit stronger, stars would burn through their fuel too quickly, leaving no time for planets to form or life to evolve. On the other hand, if gravity were weaker, stars might never ignite at all. Or consider the cosmological constant, which governs the rate of the universe's expansion. If it were even slightly larger, galaxies wouldn't have had time to form. If it were smaller, the universe might have collapsed back in on itself long ago. These aren't just minor adjustments, they're existential thresholds, and the fact that they're so precisely balanced is nothing short of astonishing. This fine-tuning has led some to speculate about the possibility of a multiverse, a vast collection of universes, each with its own unique set of physical laws. In this scenario, our universe is just one of countless others, each with different constants and conditions. Most of these universes might be lifeless, but in a few, the numbers align just right, allowing life to flourish. It's a compelling idea, one that offers a potential explanation for why our universe seems so perfectly suited for us. Yet, it's also a reminder of how much we still don't know. Is the multiverse real? And if so, could we ever find evidence of its existence? The Anthropic Principle also invites us to think about the nature of existence itself. Are we here by chance, or is there something more at play? Some see the fine-tuning of the universe as evidence of a higher purpose, while others argue it's simply a quirk of probability. Philosophers and scientists alike have wrestled with these questions for centuries, and while we may not have definitive answers, the journey of exploration is just as important as the destination. After all, the Anthropic Principle isn't just about explaining the universe, it's about understanding our place within it. What makes this principle so fascinating is its ability to bridge science and philosophy. It challenges us to think beyond the observable, to consider the deeper implications of our existence. Whether you see the universe's fine-tuning as a cosmic accident or a sign of something greater, one thing is clear: the Anthropic Principle forces us to confront the profound mystery of why we're here. And in doing so, it reminds us that the universe isn't just a collection of stars and galaxies, it's a stage, perfectly set for the story of life to unfold. Now let's step back and take in the universe on its grandest scale, a tapestry so vast and intricate that it defies easy comprehension. This is the cosmic web, the largest structure in existence, a sprawling network of galaxies, gas, and dark matter that stretches across billions of light years. Imagine a spider's web, but on a scale so immense that each strand is a thread of galaxies, and the spaces between are voids of near-nothingness. This isn't just a random scattering of stars and galaxies. It's a carefully woven framework, a map of the universe's architecture that reveals the hidden forces shaping everything we see. At the heart of the cosmic web lies dark matter, the invisible scaffolding that holds the universe together. Though we can't see it directly, its gravitational influence is undeniable. In the early universe, tiny fluctuations in the density of dark matter created the seeds of this vast network. Over billions of years, gravity pulled matter into dense regions, forming filaments, long, thread-like structures that connect clusters of galaxies. These filaments intersect at nodes, where galaxies gather in massive clusters, while the spaces between remain eerily empty, known as cosmic voids. Together, these elements create a structure that resembles a three-dimensional spiderweb, a testament to the universe's complexity and order. But what makes the cosmic web so fascinating isn't just its scale, it's the way it shapes the story of the universe. Galaxies aren't scattered randomly, they're drawn to the densest parts of the web, clustering along filaments and gathering in nodes. This distribution isn't just a cosmic coincidence, it's a direct result of the universe's evolution. As dark matter clumped together, it pulled ordinary matter along with it, creating the conditions for galaxies to form. In this way, the cosmic web isn't just a static structure. It's a dynamic map of the universe's history, tracing the journey from the Big Bang to the vibrant cosmos we see today. One of the most striking features of the cosmic web is its voids, those vast, empty regions that make up most of the universe's volume. These aren't just gaps, they're active participants in the cosmic dance. As galaxies and clusters are pulled toward the denser filaments and nodes, the voids expand, stretching the fabric of spacetime itself. This interplay between dense regions and empty spaces drives the universe's expansion, shaping its large-scale structure and influencing the fate of everything within it. It's a reminder that even in the emptiness, there's a story to be told, a narrative woven into the very fabric of the cosmos. The cosmic web also offers a window into the universe's earliest moments. By mapping its structure, scientists can trace the echoes of the Big Bang, the tiny fluctuations in density that set the stage for everything that followed. These fluctuations, imprinted in the cosmic microwave background, grew over time, amplified by gravity, until they formed the intricate network we see today. It's a process that took billions of years, a slow-motion ballet of matter and energy that transformed a uniform cosmos into the vibrant, structured universe we inhabit. But the cosmic web isn't just a scientific curiosity, it's a reminder of our place in the universe. Every galaxy, every star, every planet is part of this vast network, connected by invisible threads of dark matter and gravity. It's a humbling thought, one that invites us to consider the scale of existence and the forces that bind it all together. And as we continue to map and study this cosmic tapestry, we're not just unraveling the secrets of the universe, we're also discovering more about ourselves and the intricate web of connections that make us part of something far greater. The cosmic web is more than just a structure. It's a story, a map, and a mystery all at once. It challenges us to think beyond the familiar, to explore the universe on its grandest scales, and to marvel at the forces that shape it. And as we peer into its intricate patterns, we're reminded that the universe is not just a collection of stars and galaxies. It's a living, evolving entity, full of wonders waiting to be discovered. Now, let's turn our attention to one of the most puzzling mysteries in the history of space exploration, the Pioneer Anomaly. Picture this: two spacecraft, Pioneer 10 and 11, launched in the early 1970s to explore the outer reaches of our solar system. These pioneers of space travel were expected to drift through the void, their trajectories governed by the predictable laws of gravity, but something strange happened. As they ventured farther from the sun, they began to slow down slightly more than scientists had anticipated. This tiny, unexpected deceleration became known as the Pioneer Anomaly, and it would baffle researchers for decades. At first glance, the anomaly might seem insignificant, a mere fraction of a millimeter per second squared in deceleration. But in the precise world of astrophysics, even the smallest deviation can signal something profound. For years, scientists scrambled to explain this discrepancy. Could it be a miscalculation in the spacecraft's trajectory, a subtle error in the models predicting their movement, or was there something more mysterious at play, something that hinted at gaps in our understanding of gravity itself? The Pioneer Anomaly became a cosmic riddle, challenging everything we thought we knew about the forces that govern the universe. One of the leading theories suggested that the anomaly might be caused by thermal radiation. The spacecraft, powered by radioactive decay, emitted heat as they traveled. This heat, radiating unevenly from their surfaces, could have created a tiny but measurable push, slowing the probes down over time. It's a bit like a car coasting to a stop because its engine is cooling, except in this case, the car is hurtling through the vacuum of space, and the engine is a nuclear power source millions of miles from Earth. While this explanation seems plausible, it took years of meticulous analysis to confirm, and even then, it didn't entirely close the book on the mystery. But the Pioneer Anomaly isn't just a story about heat and spacecraft trajectories. It's a reminder of how much we still have to learn about the cosmos. Gravity, one of the most familiar forces in the universe, behaves predictably in most scenarios. But as we venture farther from Earth into the uncharted territories of the outer solar system, even this fundamental force can reveal surprises. Could there be aspects of gravity we've yet to understand, or could the anomaly point to something even more exotic, like the influence of dark matter or undiscovered particles? These questions, while still unanswered, highlight the enduring allure of the unknown. What makes the Pioneer Anomaly so fascinating is its ability to inspire curiosity and debate. It's a testament to the scientific process, a reminder that even the smallest observations can lead to profound questions. And while recent research has largely attributed the anomaly to thermal effects, it remains a celebrated case of cosmic detective work. It's a story that underscores the challenges of exploring the outer solar system, where even the most carefully designed missions can encounter the unexpected. The Pioneer Anomaly also serves as a humbling reminder of the universe's complexity. Even with all our advancements in technology and theory, there are still phenomena that defy easy explanation. It's a call to keep exploring, to keep questioning, and to remain open to the possibility that the cosmos still holds secrets waiting to be uncovered. Whether it's a subtle deceleration in the depths of space or a new discovery that reshapes our understanding of the universe, the Pioneer Anomaly reminds us that the journey of exploration is never truly finished. And in that journey, every mystery, no matter how small, brings us one step closer to understanding the grand tapestry of existence. Beyond the orbit of Neptune, where sunlight fades to a faint glimmer, lies a frozen frontier teeming with ancient secrets, the Kuiper Belt. This vast, icy expanse is like a cosmic time capsule, preserving remnants of the solar system's earliest days. Imagine a ring of icy bodies, some as small as pebbles and others as large as dwarf planets, orbiting the sun in a distant, shadowy dance. Among these frozen worlds is Pluto, the most famous resident of this frigid realm, but it's far from alone. The Kuiper Belt is home to countless other objects, each one a relic from the dawn of our solar system, waiting to tell its story. What makes the Kuiper Belt so fascinating is its role as a window into the past. When the solar system formed over 4.6 billion years ago, it was a chaotic swirl of gas, dust, and ice. Over time, gravity pulled this material together, forming the sun, planets, and moons we know today. But not everything was swept up in this process. Far beyond the reach of the giant planets, in the cold, dark outskirts of the solar system, leftover debris clumped together to form the Kuiper Belt. These icy bodies are like cosmic fossils, preserving the raw materials from which the solar system was built. One of the most intriguing aspects of the Kuiper Belt is its connection to comets. Short-period comets, those that complete their orbits in less than 200 years, are thought to originate here. Occasionally, gravitational nudges from Neptune or interactions with other objects send these icy wanderers hurtling inward toward the warmth of the sun. As they approach, the heat causes their frozen surfaces to vaporize, creating the glowing comas and tails that make comets so spectacular. In this way, the Kuiper Belt isn't just a distant, frozen wasteland, it's an active, dynamic region that shapes the inner solar system in surprising ways. But the Kuiper Belt isn't just about comets, it's also a treasure trove of dwarf planets and other intriguing objects. Pluto, once considered the 9th planet, is now recognized as the largest member of this icy family. Its discovery in 1930 revolutionized our understanding of the solar system, and its reclassification in 2006 sparked a lively debate about what defines a planet. Beyond Pluto, Other dwarf planets like Haumea, Makemake, and Eris have been discovered, each with its own unique characteristics. Haumea, for example, spins so fast it's shaped like a football, while Eris is slightly more massive than Pluto, challenging our assumptions about the outer solar system's hierarchy. Exploring the Kuiper Belt has been a monumental challenge, but one that has yielded incredible rewards. In 2015, NASA's New Horizons spacecraft made history by flying past Pluto, capturing stunning images of its icy plains, towering mountains, and hazy atmosphere. The mission didn't stop there. It went on to visit Arrokoth, a distant Kuiper Belt object that looks like two snowballs stuck together. This pristine, ancient body offers a glimpse into the conditions that existed when the solar system was just forming, providing clues about how planets and other bodies came to be. The Kuiper Belt also raises profound questions about the solar system's boundaries and origins. How far does it extend? Are there even larger worlds lurking in its depths, waiting to be discovered? And what can these icy bodies tell us about the building blocks of planets, including our own? Each new discovery adds a piece to the puzzle, helping us understand not just the Kuiper Belt, but the broader story of how our cosmic neighborhood came to be. As we continue to explore this icy frontier, we're reminded of the solar system's complexity and the enduring mysteries that lie just beyond our reach. The Kuiper Belt is more than just a collection of frozen rocks. It's a living archive of the solar system's history, a place where the past meets the present and where the secrets of our origins are waiting to be uncovered. And with every mission, every observation, we come closer to understanding the forces that shaped our cosmic home and the icy worlds that still call to us from the distant reaches of space. Now, let's travel back in time to one of the most dramatic and mysterious events in modern history, the Tunguska Event. Picture this: a quiet morning in the remote wilderness of Siberia, June 30, 1908. Suddenly, the sky is torn apart by a blinding flash, brighter than the sun itself. A shockwave ripples through the air, flattening trees like matchsticks across an area larger than New York City. The explosion was so powerful that it registered on seismic stations thousands of miles away and lit up the night sky across Europe and Asia. Yet, when scientists arrived to investigate, they found no crater, no obvious sign of what had caused this cataclysmic event. This is the Tunguska Event, a cosmic mystery that continues to captivate and perplex scientists over a century later. So, what exactly happened that day? The leading theory is that a meteoroid, or a small comet fragment, roughly 60 to 190 meters in diameter, entered Earth's atmosphere at breakneck speed. As it plunged toward the surface, the intense heat and pressure caused it to explode about 5 to 10 kilometers above the ground. This airburst released energy equivalent to 10 to 15 megatons of TNT, hundreds of times more powerful than the atomic bomb dropped on Hiroshima. The explosion flattened an estimated 80 million trees across 800 square miles, yet left no crater, as the object likely disintegrated entirely in the atmosphere. It's a stark reminder of how even relatively small cosmic objects can unleash unimaginable destruction. But the Tunguska Event isn't just a historical curiosity, it's a wake-up call. It underscores the very real threat posed by near-Earth objects, or NEO, and the importance of planetary defense. While the chances of a similar event happening in any given year are relatively low, the potential consequences are catastrophic. A similar explosion over a populated area today could devastate an entire city, causing untold loss of life and economic damage. The Tunguska Event serves as a powerful example of why scientists and governments worldwide are working to track and study asteroids and comets, developing strategies to mitigate the risks of future impacts. What makes this event even more intriguing is the lingering uncertainty about its exact nature. Was it a stony asteroid, a comet, or something else entirely? Some researchers have proposed more exotic explanations, such as a fragment of antimatter or even a microscopic black hole passing through Earth. While these theories are less likely, they highlight the enduring mystery of the Tunguska Event. Despite decades of study, we still don't have all the answers, and that's part of what makes it so fascinating. It's a puzzle that continues to challenge our understanding of the cosmos and our place within it. The Tunguska Event also serves as a reminder of the delicate balance that allows life to thrive on Earth. Our planet is constantly bombarded by debris from space, but most of it burns up harmlessly in the atmosphere. Occasionally, though, larger objects slip through, and the consequences can be devastating. This event is a testament to the importance of vigilance and preparedness, as well as the need for international cooperation in protecting our planet from cosmic threats. As we reflect on the Tunguska Event, we're reminded of the incredible power of nature and the mysteries that still surround us. It's a story of destruction, yes, but also of resilience and discovery. Each new piece of evidence, each new theory, brings us closer to understanding what happened that fateful day in Siberia. And as we continue to explore the cosmos, we're not just uncovering the secrets of the universe, we're also learning how to safeguard our future. The Tunguska Event may have been a cosmic accident, but it's also a powerful lesson in the importance of looking to the skies and preparing for the unexpected. Now, let's shift our gaze to one of humanity's most profound and enduring quests: the search for extraterrestrial intelligence, or SETI. Imagine the universe as a vast, silent ocean, and SETI as a radio buoy, tirelessly listening for whispers of life in the cosmic waves. This scientific endeavor isn't just about scanning the skies. It's about seeking answers to one of our deepest questions: are we alone in the universe? For decades, SETI has been at the forefront of this exploration, using powerful radio telescopes to sift through the noise of the cosmos, hunting for patterns that might reveal the presence of intelligent beings beyond Earth. At its core, SETI operates on a simple yet profound premise. If advanced civilizations exist, they might be sending signals into space. These signals, whether intentional messages or accidental byproducts of technology, could travel vast distances, carrying the faint echoes of distant worlds. To detect them, SETI scientists focus on narrowband radio waves, specific frequencies that stand out against the natural background noise of the universe. It's like tuning a cosmic radio dial, listening for a station that might be broadcasting from light years away. The challenge, of course, is that space is unimaginably vast, and the odds of picking up a signal are astronomically small. Yet the search persists, driven by the tantalizing possibility of making contact. One of the most iconic moments in SETI history came in 1977 with the detection of the now famous WOW signal. Lasting just 72 seconds, this burst of radio waves appeared to originate from the constellation Sagittarius and bore the hallmarks of an artificial source. Though never detected again, the WOW signal remains a beacon of hope, a reminder that even the briefest flicker of something unusual can ignite our imagination. It's moments like these that keep the search alive, fueling the belief that somewhere out there, another civilization might be reaching out. But SETI isn't just about listening for messages. it's also about understanding the broader context of life in the universe. Through initiatives like the Drake equation, scientists attempt to estimate the likelihood of intelligent civilizations existing elsewhere. This equation considers factors like the rate of star formation, the number of habitable planets, and the probability of life evolving to intelligence. While the numbers are speculative, they provide a framework for thinking about the vast possibilities. And with the discovery of thousands of exoplanets in recent years, many of which lie in their stars' habitable zones, the idea that life could exist elsewhere feels more plausible than ever. The tools of SETI have also evolved dramatically since its inception. Early efforts relied on single radio telescopes, but modern projects like the Allen Telescope Array and the Breakthrough Listen initiative use networks of antennas and advanced algorithms to scan millions of frequencies simultaneously. These technologies allow SETI to cover more ground, or rather, more sky, than ever before, and while no definitive signal has been found, the search has already yielded valuable insights. By ruling out vast swaths of the electromagnetic spectrum, SETI helps narrow the field, bringing us closer to the day when we might finally detect a signal. What makes SETI so compelling is not just the science, but the profound questions it raises about our place in the universe. If we were to detect a signal from another civilization, it would fundamentally change how we see ourselves. Are we unique, or just one of many intelligent species scattered across the cosmos? What would we say in response, and how might such a discovery reshape our understanding of life, culture, and existence? These are questions that transcend science, touching on philosophy, ethics, and the very essence of what it means to be human. SETI is more than a scientific endeavor, it's a testament to humanity's curiosity and resilience. It's a reminder that even in the face of overwhelming odds, we never stop looking, never stop wondering, and never stop reaching for the stars. The search for extraterrestrial intelligence is a journey that connects us all, a shared quest to uncover the mysteries of the cosmos and perhaps find our place among the stars. And as long as there are questions to be asked and skies to explore, SETI will continue to listen, to hope, and to dream. As we reach the end of our cosmic voyage through 30 unbelievable phenomena shaping our universe, it's impossible not to feel a deep sense of awe. We've journeyed from the incomprehensible power of black holes to the delicate threads of the cosmic web, each phenomenon revealing a new layer of the universe's grandeur. These cosmic wonders are more than just distant curiosities, they are windows into the very fabric of reality, inviting us to question, explore, and marvel at the infinite complexity of existence. What makes these phenomena so extraordinary is not just their scale or their beauty, but the way they challenge our understanding of the universe. They remind us that for every answer we uncover, a dozen new questions emerge. The more we learn about the cosmos, the more we realize how much we still have to discover. It's a humbling thought, but also an exhilarating one. The universe is not a static place. It's a dynamic, ever-evolving tapestry of mysteries, and we are privileged to be part of the story. This journey has also reminded us of our shared humanity. Whether you're an avid stargazer or someone who's just beginning to explore the wonders of space, these cosmic phenomena connect us all. They spark curiosity, ignite imagination, and inspire us to dream bigger. When we look up at the night sky, we're not just observers, we're participants in a grand cosmic adventure, one that stretches across billions of light years and billions of years. As we wrap up, I encourage you to take a moment to step outside and gaze at the stars. Let the immensity of the cosmos sink in, and let it remind you of the endless possibilities that lie beyond our world. Each star, each galaxy, each cosmic phenomenon we've explored is a testament to the universe's boundless creativity. And while we may never fully unravel all its secrets, the pursuit of knowledge is a journey worth taking. Thank you for joining me on this exploration of the cosmos. If these phenomena have sparked your curiosity as much as they've sparked mine, let me know in the comments below. What cosmic wonder captivated you the most? And if you're eager for more adventures into the mysteries of the universe, don't forget to subscribe and hit the notification bell. The universe is vast, and the discoveries are endless, so let's keep exploring together. The stars are calling, and the journey has only just begun.